what we did last lecture was the recap, right? And we saw the first item of the recap for the final was random variables. And we saw that there are two random variables, continuous and discrete, okay? We worked on the discrete PDF, meaning that that's the probability distribution function, which is a table. It could be a histogram as well. And we worked as well as in the CDF, okay? Then we saw the fourth item, which is creating new variables. We saw that you can create linear ones, not linear, it's what it's called an affine transformation. In this course, I'm calling it linear. It's not true. Mathematicians would kill me. But it's just to remind us that this is the equation of a line, y equal to ax, right? So this situation is a little bit easier. If it's not this situation, just be careful. It might be ambiguous, and you have to pay attention on what you're doing. Then we saw statistics. We saw expected value, variance, and standard deviation is just the square root of the variance. So if you want the standard deviation, you will have to calculate the variance. We did some exercises. We saw the binomial random variable, which is this stylish b. It's just a notation. And the stylish b says to you, when you see a stylish b as a variable, you know that you're doing a repeated trial. And this notation is overloaded with information. In the parenthesis, n is the number of trials, p is the probability of success. And we stopped here, item 7. Okay? So now we're going to recap continuous random variables. What is that we saw is that continuous random variables, they cannot have a PDF that's a list, because you cannot list the values that a continuous random variable takes on. So in the end of the day, the only way to do the PDF, to show the probabilities of the numbers that the variable can assume, is using a graph. And it's using a histogram. But in this case, the histogram of a continuous random variable becomes a smooth curve. Okay? If you go back to the material, the bins start to being very close to each other, that at some point they kind of fuse and you have like a smooth curve. Okay? How can we calculate probabilities using this PDF? Now the PDF changes its name to probability density function. And it's because actually the probability is the area. Just as in the histogram, you would have the area of the bins. You would take the area of the bins to calculate the probability. Now the probability is the area under this curve, this smooth curve. So the probability of an x, of a particular x, being less or equal to little x, you will have to calculate this curve here that I'm highlighting, okay? And another thing that's very important that we saw is that the probability of x being equal to a particular number, little x, is actually 0, okay? So what does this mean? It means that to calculate the probability, you have to find the area. You cannot go and say, oh, the probability of little x is this point here, and it has value, I don't know, 0.2, 20%, right? It's not that way. You cannot have a single point to calculate the probability. Well, why is that? Well, if you say that, let's say that x is 4, little x is 4. So what's the probability of your x being equal to 4? You're assuming that 4 is 4.00000 to the infinity and beyond, right? And we don't have the precision, even if you're measuring, to guarantee that you have 4.0000 to the infinity and beyond. It might be that it's 0.00001, right? So it is very unlikely that your random variable will assume something that is just so precise, okay? So that's why if you want to find if we want to find the probability, we have to use a range. So the probability of x being bigger than A, less than B, right, is the area between A and B. Okay, so it's this area here. So you can think about this. Oh, I want the probability of my height being 1.63. Well, it will never be 1.63 because 63 it's too precise. But you could calculate the area under the curve of being between 162.9 and 163.1. Okay, so around 1.63. Okay, that's what we saw. And because of this property here, that the probability of being equal to a number is 0, we can always say that the probability of being less than or equal to x is actually just, you drop the equal sign, because it won't make a difference, right? As well as, like, for example, x between A and B will be exactly the same thing as between and equal to A and B, because the equal doesn't matter. Okay? So this is what we learn about continuous random variables. Let's practice with this, an exercise. Suppose that y is a continuous random variable with a probability density function. Oh, sorry. Sorry for this. This is not y. This is x. Suppose that, sorry for this. Suppose that x is a continuous random variable with a probability density function f of x equal to 3x plus 3 over 50 when your x is between -3 and 7 and 0 otherwise, and evaluate a probability. Okay? So when you see this, first of all, it's a continuous random variable, and the PDF is given by an equation. Well, it is the case because actually a PDF of a continuous random variable is a curve. So actually this is the equation of the curve, of the smooth curve of your PDF. Okay? And so what is the problem saying? Between -3 and 7, so between -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. Between -3 and 7, my curve follows this rule, follows this equation, okay? And after or otherwise, it's 0. So my PDF, think about plotting my PDF. It is 0 otherwise. So it's 0 off of the interval -3 to 7, okay? And between -3 to 7, it follows the curve. It follows this equation, okay? Now, this equation is given by f of x equal to x plus 3 over 50. This has a special, it's a relationship of a special type, because you can think about separating both terms, and this is 1 over 50 times x plus 3 over 50. Which kind of relationship is this? It's the equation of a line, right? So it's of the type ax plus b. So my f is ax plus b, okay? So it's an equation of a line. So for sure there will be a line here between -3 and 7. How can I draw that? Well, think about this. My line, line connects 2 points, right? So let's evaluate my curve. Let's evaluate what would be the value of my smooth curve when my x is in 3, like the lower part of the interval. So f of -3 will be -3 plus 3 over 50. This is equal to 0. So it means that my line sits on 0 when my x is minus 3. And if I evaluate in 7, so let my x be 7, this will be 7 plus 3 over 50, which is 10 over 50, or 1/5, right? So this is 1/5. So it means that my curve will have a value of 1/5. When my x is 7, my curve, which is a line, will have this value. So because it's a line, it has to pass on both of these points, right? So it's this line here. Okay? And it actually ends. I did it bigger than I was supposed to do. It ends here. So if you take a look at the PDF, this is it's kind of a histogram that was smoothed out. The PDF of this variable x is actually, it's a curve. It's a smooth curve that comes 0 up until 3. Then it starts growing, and then it suddenly drops to 0 in 7. Okay? This is my smooth curve. So the question is this: what's the probability of x being less than 3? So I want the area under the curve, right? The area under the curve gives me a probability. And I want the area of under the curve for all the x's that are less than 3. So the axis could be -4, -5. So I want the area of all under the curve of all these axes here until what? Until 3. Should I include 3? The variable is continuous. So I can, because it's easier to draw, because in the end of the day, the probability of x being less than 3 is the same as including the point 3. It's completely the same. So I will include, just because it's easier to know where my graph stops. Like my area will stop at 3. Okay? So what I want is the area, like the area under this curve. Obviously that this blue part here has area 0, right? Because the curve is 0. So the curve doesn't have a height. The height is 0 of the curve, and so I cannot calculate this area. So I don't mind this area. This area won't make a difference. So what I need is to know the area of this triangle. And just to recap, the area of a triangle, so the area of a triangle is the width times the height over 2, right? What's the width of this triangle? Well, it goes from -3 to 3, so it's 1, 2, 3, 4, 5, 6. So I have the width, so the probability of x being less or equal to 3 is the width, that is 6, okay, times the height over 2. But do I have the height? The height of the triangle is this, right? This is the height of my triangle. Do I have this information? No. Can I find this information? Yes, because this, again, this f of x is the equation of the curve, or in this case it's a line. So this f of x it's spitting out to me the value that curve has in a particular point x. So think about this. I want to find the value of f of x, right, of this curve f of x, when my x is 3. So I will evaluate f in 3. So this will be 3 plus 3 over 50. This is 6 over 5. Okay? So this is This is the height. My curve, my smooth curve, will have a value if I were to draw the y-axis, like the axis here. If you measure this curve, will value 6 over 5, sorry, 6 over 5. Okay? Yeah.
How is it 6 over 5?
6 over, so no, it's over 50, right? So 6 over 50, I'm sorry. 6 over 50, sorry for that. Okay. So I know the height. Now I know the height, so I just complete my calculation. This is 6 over 50. So this is 36 over 50, right? Over 2, so this is 36 over 100. Okay? So it's just working out the fractions. Good? Questions about this? Like continuous random variables. You will have, if they are asking you to calculate a probability, they will have to give you an equation to find the area under the curve. And it will usually be, or it will be this triangle, or it could be f of x. Another example could be f of x equal to, I don't know, 5. So when you plot your x, your f of x doesn't change with x. So x is minus 2, minus 3, minus 4. So minus 2, minus 1, 0, 1, 2. The f of x is not changing. Okay? And they will ask you to calculate the area between 1 and 2. So it's this rectangle. Okay? So there are two possibilities for this course, is triangle or rectangles. Okay? Good? All right. So now we can go to item 8 of our recap, which is good approximation. What is this? Well, think about this. You have an x that is it's a discrete random variable. Okay? It's the blue curve. And you plot the histogram. You plot the PDF as a graph. So you have the bins centered. You have these bins centered in 0 and centered in 1. Okay? And I'm asking, oh, what's the probability of having 0? So let me zoom in. I think it's worth it. So let me zoom in and let's analyze. Oops. Let's analyze this. You have the histogram and you want the area between 0 and 1. So you will include the bin, all right, of 0, because remember the histogram, that bin that is centered in 0 gives you the area or the probability of your discrete random variable being 0, and you will include the 1, okay? Now, sometimes you don't have this information, but you have a y that is a continuous random variable. So now it's a continuous random variable that is a good fit, meaning that the variable kind of, it has almost the same figure. It's smooth. It's not bins. It's smooth, but it kind of encapsulates and fits the distribution. So what you're going to do is I don't have the information to calculate these areas in the blue world. Can I calculate this area on the yellow world? Yes, you can. So you will select an interval. So I have the yellow world here. You will select an interval AB that makes the area the same as the pink area. Okay? So in this case, you wouldn't select 0, 1 because they are in the middle of the bins. You would select from here to here. right? You would select from here to here so that the area is the same. And why would you do that? Well, because the discrete random variable cannot assume a half. It can't. Remember, discrete random variable, they jump between values. This is a toss of a coin, for example. It's 0 or 1, you don't have a half. But the continuous random variable can assume any number. So when you want to select the same area, this is the half of the interval, and this is 1.5, right? So, and this is minus 0.5. So you're going to select minus 0.5 to 1.5 in the yellow world, okay? So the steps are this. Do a mock histogram. Find the interval that gives you the same area, okay? This is what we saw. So let's do an exercise so that we can recap. So random variables, discrete random variables, PDF and CDF. We created new variables. There are two things that are important. If the relationship follows a kind of equation of a line, it's kind of easier. If not, just be careful because it can be ambiguous. We saw the concept of expected value, right, or mean. We saw things about the binomial distribution. Oh, we saw variance as well, right? So we calculated the variance. And actually, I forgot, this is what I have to amend. I forgot to say that there's a third, statistics, that is just the square root of the variance, and it's called standard deviation, right? So this is just, I just forgot to put the equation there. So if you're asked the standard deviation, there's no other way. You will have to calculate the variance and then just square root the result. Okay, so it's just a simple square root. We saw the binomial random variable is just it's just a notation, right? Where it's like an overloaded notation. You have the stylish B tells you that you're doing a repeated trial. The first term in the stylish B is the number of trials, and here is the probability of success. Okay? And we stopped there. So we stopped at item 6. Okay? And now we're going to item 7 of our recap. We're going to talk about, more specifically, about continuous random variables. Okay? So continuous random variables, they are, let me just find it here because I had this recap before. So the continuous random variable, what happens is the PDF cannot be listed. It cannot be a list. So it is a graph. It has to be a graph. So the continuous random variable PDF is inherited from the histogram. And at some point, that all those bins actually get transformed into a curve, a smooth curve. So the PDF of a variable x, so this is the probability, not the probability, I'll call it f of x, right? This is your random variable x. This is a smooth function. And f of x is called the probability density function. So the name changed slightly. First we had, for discrete random variables, we had probability distribution function. Now we have probability density function. Okay? So in the end of the day, it's like if you imagine, I'll try to show you the video today. If not, I'm going to post it on OWL. You can imagine that bins getting very, very close together. So the points in the bins, the lines are kind of becoming points and you're connecting all of them. You have a smooth curve. Okay, so the histogram turns out to be a smooth curve. What is important for us to remember is that the probability is not in the curve, but it's actually on the area under the curve, right? So if we want the probability of x being less or equal to some number, let's say little x here, okay, what we have to do is to find the area under the curve, okay? So this is the area under the curve, and there's one more detail. The probability of something being less than or equal to x is just the probability of that x being less than that number. You drop the equal, right? Why is that? Because the probability doesn't exist if you're talking about a specific number. So let's say that this is 2. Well, what's the probability of being 2? Well, 2 is 2.000000 to the infinity and beyond. And actually, you cannot, if you're measuring, you will never know if the last atom, like if the last digit, the millionth digit is 1, right? So it's very unlikely that you assume exactly a value, but you can find the probability within a range, right? So that's why we use the less than or greater than kind of notation. So the probability of x being equal to x is actually 0, okay? And if you want to, again, because it's the area under the curve, if you want to find the probability of, I don't know, your x being between a and b, you take the area under the curve between a and b. So p of x, the probability of x being greater than a and less than b is equal to the area between a and b. Okay? This is all we did on continuous random variables. So let's do this exercise here. This exercise states this. Suppose that y is a continuous random variable with a probability density function, f of x. So this is f of x, let me put it this way, is equal to x plus 3 over 50. Okay? The probability density function is this when x is between -3 and 7. Okay? And it is 0 when, like, to all other x's, all other y's, okay? So f of x can be 0 if I'm not between -3 and 7, okay? So let's evaluate the probability of x being less than 3. That's the question. So first of all, when you see these types of functions and you're asked to calculate a probability, you need, and it's a continuous random variable, and you will see this in several tests, you have to look for the area, because that's the way you calculate probability. In continuous random variables, you have to look to the area.
This might be off topic, but when I was going through the practice exam and I saw something, sometimes it was like a rectangle, sometimes it was a triangle.
Yeah.
And how are we supposed to know if it's a rectangle or a triangle?
We can talk, yeah, I will let you know. Let me finish the triangle, and then we can do a version with the rectangle, okay? All right, so let's say that I'm going to plot. So when you see that, you need the area. Other thing that is very important, do you recognize what type of relationship is this? What type of smooth curve is this one? It's the equation of a line, right? This is the equation of a line. Why? Because it follows this form here, right? So your y, or you can call f of x y. It's the same thing, right? So you will see some exercises with f of x, which is just a new variable. Some exercises you will see, oh, a y, it's fine. So in the end of the day, a here, you can write f of x being as x over 50 plus 3 over 50. So your a, your coefficient a is 1 over 50, that multiplies x, and your coefficient b is 3 over 50. So it's equation of a line, okay? So when you see that, you will draw, because you need an area to calculate the probability. So what we're going to do is between -3 and 7, so -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 7, right? We have that relationship. We have a line, okay? And out of that range, we have my density function is 0. So this is my curve is 0 out of the range, okay? It values 0. And inside the range, it is a line, okay? So it is a line. How can I know how to draw this line? Well, let's evaluate. A line connects 2 points, right? So let's evaluate the line in the first part of the interval, in the first limit, in the lower limit, and on the upper limit. So what value would have this curve when x is -3? Well, when x is -3, so I'm evaluating f, when x is -3, this is -3 plus 3 over 50. This is 0. So my line right here in this point touches 0. Okay? And I'm going to calculate or evaluate my function, my smooth curve, when x is 7. So I'm going to substitute x by 7. 7 plus 3 over 50, right? This is 10 over 50. This is 1/5. Okay? So when my x is 7, right? When my x is 7, my curve will actually be 1/5. So in the end of the day, if a line connects 2 points, I need to connect both of these points. This will be hard. I need, 1/5. I will need to connect both of these points. Okay, so this is, my smooth function is this. It comes from 0. It starts growing, okay? Starts growing, and then it drops instantaneously to 0 and then goes on. Okay, this is the smooth function. Let me draw the axis here. That I forgot the other axis. -3, -2, -1, 0. So this is the axis here. So what I just construct is a PDF, is a probability density function of a continuous random variable. Okay? Great. What should I consider to calculate the probability of x being less than 3? Well, it's the area under the curve, right? So if it's the area under the curve of things that are less than 3, I have to calculate the area under the curve of things of this curve less than 3. So this area here, do you agree it's 0? Because like the function is 0, you don't have you don't have a geometric thing there to calculate an area. So you will keep going from 3, -2, -1, 0, 1, 2, 3. Okay? So let me just put the -2, -1, this is 0, 1, 2, and 3. So what you want actually is to calculate the area under the curve of values of x being less than 3. So you would want all this area in blue, okay? It's all this blue area that I want. Again, I want this blue area, and because this is linear, okay, because this is linear, which we call actually an affine transformation. If mathematicians heard, like if the math department hear me saying linear, they will kill me. It's called an affine transformation, okay? But here we call it linear just to remember ourselves that this is an equation of a line. Because this is an equation of a line, then it's easy because this forms what kind of shape? A triangle. And we know how to calculate the area of a triangle, right? The area, so the probability of x being less than 3 is this area. Well, up until -3, right, like -4, -5, like up until this, the area is 0. So I don't have to mind that area. After that is this triangle here. So what is the width of the triangle? Well, it goes from -3 to 3. So 1, 2, 3, 4, 5, 6. Right? It has a length of 6. This width here is 6 times the height. Okay? So this is the width here. This is the width. So just to a side note, the area of a triangle is the width times the height over 2. So this is the width, and the height is this, right? Do I know the height here? No, I don't. Oh my God, right? So I have the height over 2. The over 2 is okay, but I don't have the height yet. So what should I do to find the height? Well, you have the equation of this smooth function, right? You have the equation of this line. So you can evaluate the line and the equation when your x is 3. And then you will have the value that your line assumes. So what I'm going to do is to find the height. My height is actually my function evaluated in 3. And this is 3 plus 3. So let's put it in the equation. This is 3 plus 3 over 50. This is 6 over 50. So it means that the line, or my function f of x or y, will assume 6 over 50. Okay? So I just found that this is 6 over 50. Okay? Let me put it better. This is 6. So this is 6. I'm going to put it this way. This is 6 over 50. And then you divide everything by 2. Meaning that you divide this side and like this side here, right? You divide by 2. This is 3 times 6 over 100. Okay? This is 18 over 100. Yeah.
I'm so sorry. I'm confused where you got the height from, though.
The height?
Yes, if you mind just going over that.
Yeah, so this equation here, this equation is what we call a formation law. This f of x is the value of the curve, right? You're forming a curve, and the curve will assume values depending on x, right? So if you want the value of the curve here when x is 3, so this is x, and your graph is plotting f of x, right? So my graph is plotting f of x to know what value my curve assumes in 3. I substitute the value of x by 3. This will give me the value of f of x, which is the curve. So the curve will touch this point. The curve, which is a line, will connect this point, this point, this point. So the curve will be will take on the value of 6 over 50. Yeah.
Oh, so I'm just double checking. So if
Yeah.
you put 3 is greater than x, you put that 3 into the equation to get that.
Because 3 is greater than x? Sorry.
No, just like the probability difference.
Oh yeah, because you want the area under the curve of a smooth function, right? Of when x is less than 3. So it's the area under the curve of all your axes, of all the axes valuing less than 3. So it's the blue area that you want. Okay? Why do you include 3? Why would you include 3? Well, you're saying that this is less than 3, but actually it's the same thing, right? This is actually x, the being equal to 3 is, it doesn't matter if you include or not include 3. So you will actually include 3 to make your life easier here to calculate the area. Okay? Good? All right. So this is this is worth three marks in the test usually. There is a problem when they give you a function and the function is a constant. So your function or your PDF, I don't know, it's like 5. Okay? So if you graph this, your x minus 3 minus 2 minus 1 0 1 2 3, the PDF, the smooth function is always, it's not a line. Actually, it is a line, but it doesn't depend on x. It's always what? 5. It's always 5, right? So if x is minus 3, how much it values? 5. If x is minus 2, 5. If x is minus 1, 5, 0, 0, 1, 2, 3, whatever. This is the smooth function that you're talking about.
And that would be a rectangle.
Yeah, so then the question would say, oh, what's the probability of being between 1 and 3? You would have to select this area, and that's a rectangle. Okay? Good? I think there's one example of this on 2021. Just I'm not sure if this is, but there's a past test that has a rectangular problem. Take a look at it, and you will see that they will give you a function that is just a line, and they will ask you the probability of being between two things. So what's the area of a rectangle? It's width times height, right? So you just do this times that, which is easier, right? Because you know the height already. What's the height? What's the height? 5, right? This is 5. And so it's just easy multiplication. You don't even need to evaluate. So the probability of x being between 1 and 3 is equal to 10. Right? Okay? Questions about this? We're good? Yeah, sorry.
So if the question asks you, and it gives you essentially an equation of a line that asks you for 1 point on the line, is that an indication that it's going to be a triangle, and then it gives you a constant asks for 2 points, and it's a rectangle?
Yeah. Good. Exactly. All right. So what else did we have we seen on continuous random variables? So this is item 8 of the recap. So item A of the recap tells us about what we call a good approximation. Okay? So this is good. We talk about good approximation. Just to recap, with a discrete random variable, you have a histogram, and sometimes you don't have the histogram to calculate the area, okay? And you're told that there's a smooth curve that fits meaning that it kind of, it has the trend of that histogram, okay? It fits very well, so you can approximate the area of whatever you're calculating by calculating the area under the curve, under the smooth curve, okay? So let's say this. Let's say that x is my discrete random variable, and let's say that y is my continuous random variable. And y is a good fit, or a good approximation. Let's say that I want the probability of x, so let me see, 0, 1, of x being 0 between, let me do this, between, so this is 0, this is 1. I want the probability of x being between 0 and 1, right? If I were in the discrete world, what would I do? I would just calculate the area of this bin and the area of this bin. Do you agree? But sometimes I don't have these values, so I would have to take just the continuous one and then select an interval that gives me a similar area. Okay? So when we do a good approximation, all we're doing is actually selecting an interval. So we have to select an interval on the continuous world that approximates the discrete area. Okay? And it will depend on the exercise. You will have to draw a mock histogram. So the steps are this. Draw a mock histogram, right? Then find the interval on y, on the continuous variable. Okay? That's it. So let's do the exercise so that we can go. We will do the exercise and recap like on the go. So this is what we are seeing. Suppose x is a discrete random variable that takes on values -5, -5, -5, 10. Oh, this is -10. I'm sorry. This is -10. -10. -10, -5, 10, 15. If y is a good approximation of x, what probability would be used to approximate the probability of x being greater than 0? Okay? All right. So let's find the interval first. I'm going to draw the mock histogram. I was told that my variable could assume -10, -5, 10, and 15, right? So if I had a histogram, I don't, right? I don't have. I'm just drawing a mock histogram. But if I had, my histogram would be something like this. I don't know, like I would have my bins centered in the numbers, and they would be touching each other, right? This would be, for example, a mock histogram. Okay? Now, what do I want? Well, I want the probability of this random variable being greater than 0. So let me find where is 0 in this graph. Okay, where is 0? Well, this 0 is here. So we are in between this bin here, right? It meets in between -5 and 5, -10 and 5. So this length is 5. Half of the way is 2.5 for each side, right? So this is meeting in 7.5. Okay. Now this bin it's larger. Okay, this bin here is larger. This bin here will be touching It will be touching, so this is, we have 15. Oh, geez, I forgot to draw the 0. I'm sorry, guys. So sorry, I forgot one interval here. I forgot the 0, then the 5, then the 10. Sorry for that, just forgot. Okay. So this is minus 0.7. This one is meeting in minus 0.5. This one is meeting in 2.5. This one is meeting in 7.5, right? So what I would want, if I was in the discrete world, was to have x greater than 0. Greater and equal to. So I would, if in the discrete world, I would select this bin, because this bin gives me the probability of my variable being 0. I would select this, and I would select this, right? This is what I would do. Good? But I don't have the histogram. What I was told is that I have a y that is a good fit. So I'm just going to draw. Usually you can draw the way you like. Just kind of try to keep the trend of the histogram like this. So you have a curve that kind of gives you the shape of the histogram. Now look at this. This is this is y, okay? And you can think about the histogram as being a host histogram. I don't have it. It's just there like in the background. It's just ghosting. But I would have to select an area on the continuous random variable that is equal to the blue one. Okay? How would I select the interval of y? So here is, like, this is my variable y. Would have to take on what values? Well, I would have to take here, right? I would have to, my random, the continuous random variable would have to start in minus 2.5, right? So that I can take this piece, and it would have to end where? In 12.5, okay? That's the only way that I'm taking the same area. Now, why would you do that? Well, think about this. The blue variable cannot assume 2.5 or minus 2.5. It is discrete. The only values that variable can assume is minus 10, minus 5. The variable jumps, right? X jumps. Although you have the histogram, if you remember the histogram, each bin gives you the probability of its middle number. It doesn't mean that the discrete variable can assume more than that. The discrete variable, the x, the yellow x, cannot assume 2.5 minus 2.5, right? But y can. Y can assume those values. So that's why, to have the same exact, not exact, but very good approximation, your y can value 2.5, and that's where you start. And you will end on 12.5, so that the area that you're selecting here, this area here that I am, how do I say this, highlighting, is the same as the blue one. Okay? So in the end of the day, the probability, right, of having, where is it? My mouse is here. So this is the probability, right, of, oh, and actually, geez, I just did something, I just forgot one thing. It's greater than, so it doesn't even stop, right? It doesn't even stop. So actually the blue area here goes forever there. You don't even stop, okay? So you don't have this, the first stopping thing. You just keep going. So the probability is y greater than or equal to minus 2.5. Okay? Good? So just to kind of wrap it up. Construct the mock histogram and kind of highlight the area that you would like, right? You would like an area on my like your little histogram, your ghost histogram to be the blue area. Okay, so this is the blue area. Then draw some kind of curve. Okay, draw some kind of curve and say, what area should I select? Okay, what area should I select? Well, the area you should select is greater than minus 2.5, and it would stop in 15, right? So it would stop in 15. Yeah.
I was just asking if you were gonna put the numbers in between.
Yeah, I will. So this is y is equal to, I just forgot I drew wrong the first time and then just got wrong. Okay, so this has to be greater than minus 2.5 and has to be smaller than, well, actually it's not even 15. What number is this? Which number is this? 17.5, right? Okay? So this is the interval. Okay? So this here is 12.5. This is 17.5 because 15 is in the middle. So that's what you're doing. You're selecting in your curve, in your pink curve, you're selecting the same area. Okay? Good? All right. So this is all you have to do with good approximations. So this is a little z, and you will read it directly from the table. So let's say that you want the probability of your z being less or equal to 0.21. What you would do in the table is you would go to the column that has a 0.2, because this is the first digit, and you would go to the column that it's 0.01. Okay? If you sum up both of this number, you will have 0.21. So you will go through this row, go through this column, and the figure that is sitting here is the probability. Okay? Now, the z table, you can only assess the values of the probability directly if we're talking about the z normal. Not all normals are the z normal. The z normal stands for the standard normal. It means that it has mu 0 and standard deviation 1. So the bell curve sits in 0 and has a standard deviation, a wideness of 1. Okay? Most of the bell curves are not like this way. Most of the bell curves, the normal bell curves, or what we call non-standard, has any mean. I don't know, it could have a mean of 10 with a standard deviation of 5. So they're the same shape, but they're not in the same place, okay, in the number line. And they don't have the same width. So if that's the case, and you need the probability, so how can I find, so this is not z, this is a variable x. It's a non-standard normal. How can I find the area under the curve? We saw a procedure for that called standardization. So I will standardize my bell curve. Okay, my bell-shaped curve. So what am I going to do? It's a procedure. You take P of x. So you want to know what's the probability of your x being less than little x. Okay? You want to calculate the area in blue, right? But this is not a z. You cannot do this procedure here. You take this probability is equal to, take the both sides of your inequality and subtract the mean and divide by the standard deviation. If you do that on both sides, this is a mu by the standard deviation, this is the same thing. And mathematicians proved that if you do this in whatever normal you have, in whatever x you have, this will become z. The left-hand side will become z, okay? And the right-hand side will become a score or a little z that you will be able to look up on the table, okay? So let's do an exercise so that we can understand this. And here's the exercise. The length of a dog's tail can be modeled as a normal random variable with an average length of 11 and a standard deviation of 1. Okay? So obviously that this is not a standard normal because it has mean 11 and a standard deviation of 4. Okay? Oh, of 1, sorry. Of 1. Meaning that most dogs have a tail around 11. Okay, so think about an area. I want to have the area of a tail of 3 centimeters. Well, the probability is very low. Like just pugs and bulldogs will have like this short little tail. And what's the chance of having a super long tail, like more than 30 centimeters? Well, you can have some dogs, but it's not usual, okay? So the biggest kind of chunk of area comes around the mean, meaning that most dogs will have something around 11 centimeters. Okay. Now, the question is, what's the probability that a randomly selected dog has tail less than 10.8? So I'm asking this. This is what I'm asking. Okay? What's the probability of x having less than 10.8? Can I use the curve directly? The table directly, the z table? No. Why not? Because this is not the standard normal. What do I have to do? I have to standardize. So what am I going to do? I'm going to do the procedure. So this p here that I want is actually equal to a p where I'm going to do a manipulation. I'm going to take 10.8 and the x, and I'm going to subtract on both sides the mean. The mean of the tails are 11. Is 11. And then I'm going to divide by the standard deviation with, thank God, is 1, right? So that we don't have to calculate this. Oh, man. Sorry. Okay. So this is what I'm doing. I do the procedure. And as I do the procedure, it is proved that your left-hand side will become a z. You can always do that. You will always become a z. And your right-hand side, which is 10.8 minus 11 over 1, is just a number, which is your z-score that you can now go and look at the table. It's actually minus, right? It's 10.8 minus 11. Okay? Good? Now we have a problem. And that will be the 10th item of your recap. Why do we have a problem? Can I look up this table? Can I look the minus 0.2 on this on the table? No, I can't, because the table that you will be provided is actually a positive table. So it's a z table like this, where you can look at the little the z-scores, you don't have a negative one, right? So this comes up to we stopped here at p of z less than minus 0.2. How can we work ourselves out of this? So we are still in the same exercise. We stopped here, p of z. So the probability of having a tail less than 10.8 is equal to the probability of having a z less than or equal to minus 0.2. Okay? You can drop the equal if you want. So I have to work myself out of this. And there are two properties that gives us this this way of kind of changing things. First property is the symmetry property. You can see here that the area under the curve of a z, so now this is the z, right? So you can see it's centered in 0. The black curve is the one that I want. It's the probability of z being less than minus 0.2. But because the bell shape is symmetric, I could also say that my area under the curve of an x being more than 0.2 is the same. So this tail is equal to this tail here, like this black area is equal to the blue area. So this is a symmetry property. And you could work that saying, oh, the probability of z being less than minus 0.2 is equal to the probability of z being greater than 0.2. Would this property help us? Like, could I go to the table and look at directly? No, because the table never gives me a probability of z being greater than. Okay, so this is a property, and sometimes it will be useful, not in this exercise. The other property that we have is the property of what I call the whole property. Okay? So what the whole. So what are you thinking, what we need to think about is this. Okay, I want the area, the black area, which I know already is the blue area, right? It's the same area. How can I find the blue area here? Well, use the whole symmetry, the whole property, sorry. You will think about this. Imagine the whole area minus the pink stuff. You would be left with exactly what you want, right? So this is always like 1 minus and the probability of z being less or equal to 0.2. Now, both of this reasoning together will give me the answer. Why? Because now I can go and look up in the table. So in the end of the day, this p, let me give myself some space here. This, oh wow. This p here, okay? So this p of z less than or equal minus 0.2 is actually, it could be written as p of z greater than 0.2, which is equal to 1 minus the probability of z being less or equal to 0.2. Okay? So all of this are equal. This step is the standardization step. Now this step here and the last one, they're all using the properties. This one is the symmetry property, right? This is the symmetry property, and this is the whole property. So I first use the symmetry and then the whole, and then I land in something that I can go to the table and look at it. Okay? Now, if I go to the table, it's z less than 0.2. How can I do that? Column 0.2, right? what is, sorry, row 0, 2, what's the column? It's the first one, is 0, 0, right? Because it's only 0, 2. So it's this figure here that you're seeing, which is 0.5793, which is 0, 2 with 0, 0. This figure here is the probability. So this is 0.5793. So this is 1 minus 0.5793. Okay? This will be approximately 0.42. Questions on what we did? All good? All right. So there is a kind of more algorithmic way of getting yourselves out of some situations that you cannot use the table. And it's this. You can go to the side of your test and you can draw 3 boxes. You can draw three boxes. And on these 3 boxes, you will write subtract from the whole. On the next box, you will say change sign of z, or switch, or flip, maybe flip is better, the inequality, flip inequality. You're going to do this like on the side of your test. And you, as long as you choose 2 moves within these 3 moves, you are good. The probability that you're looking at is equivalent. So think about this. Think about this orange. Think about, I chose this one and this one. Okay? What was I looking? I was looking to find a p of z less or equal to minus 0.2, right? So I chose these 2 steps. First of all, change the sign of z, of little z. So I come here and I change the sign of little z. What else? Well, flip the inequality. I will flip the inequality. So just if this was less than, this will be greater than. Okay? And it's true. It is true. It is true from the symmetry property. Okay? Then you will go and think, oh, this won't help me, right? Because I don't have greater than. That's okay. You can just test another combination, right? It's really fast to do these tests. If you don't want to reason, you can just have this. For example, we could change the sign of z and subtract from the whole. So this probability will be, first of all, subtract from the whole. So you take 1 minus what you had, but then change the sign of z, the little z. So you're going to go positive. Oh, that is what I reasoned with the properties. I've definitely found 2 moves that will land me in something that I can do. Okay? I could have chosen change the sign of z. I could have chosen yet another combination, right? Which is change the sign of z and, subtract from the whole and flip the inequality. And you can do that. So it would be, let me do here because I will delete that. It won't help anyways. So you have this, and let's do this, both these moves. You subtract from the whole, and you flip the inequality. So you do z greater than minus 0.2. Of course, that this move Won't help at all. First of all, because I don't have more than, greater than, and also I don't have a negative number in the z-score. So there will be moves that won't help you. There will always be one move that will, like a pair of moves that will help you. So if you don't want to reason about the symmetry and, you know, like all of these steps that we made, you can go to the side of your test, do the 3 boxes, and just very quickly test what would help you. Okay? Questions? Are we good? All right. Now, we are going to do an exercise yet on standardization, but it's a different kind of exercise. Okay? So we're talking about standardization still. The exercise says this: suppose x is a normal random variable, which we are told has a mean of 10, and for which the probability of that variable being less than 12 is 89.25. Determine the standard deviation of x. Okay, so stop there. What are we talking about? We're talking about an x that is not a standard normal. It is a normal, right? It's set that is a normal, but it's not the standard normal. It's not the z. Okay? And it has a mean of 10. Okay, fine. So the guy came and told us this: the probability of this variable being less than 12 is something. Okay, how on earth the guy got this number? The guy got this number by standardizing. There's no other way. If you don't have a standard normal, you have to standardize. So this value here that the guy gave me was found by doing a standardization. So whatever I need to do, determine whatever, determine sigma, the standard deviation, whatever I have to do, I have to consider that this variable x was standardized because the guy found the probability. So what did the guy do? The guy did this. The probability of x being less than 12 is 0.8925, right? But the way he found this number, it has to be by standardization. So it has to be by doing p of x less than 12, which is equal to the process of standardization. Let me remind you how we do it. We take mu, divide by standard deviation, less than or equal to the little x minus mu over the standard deviation. This is the process of standardization. Okay? So the guy took from this side, the guy subtract the mean, which is 10, right? It was given to you. And from the other side, it subtracted the mean as well, and it divided by the standard deviation. And this, the guy found that was 89.25, right? So we know that when we do the standardization, the left-hand side becomes what? Becomes the standard normal, right? What about this guy? Well, this guy becomes a number. I don't know which number it is, but it's the z-score that I will look at the table, right? And when I look at the table, the guy found this probability. So how can I find the standard deviation? I want this guy. How can I find this guy? Well, think about this. If I go to the table and I find the probability that like if I find this figure in the table, I can figure it out what column and row the guy looked at, right? After standardizing. And then I can, because little z is this, I can derive sigma. So let's do that. So the guy, again, the guy had a non-standard normal. He found a probability. The way he found the probability is always by standardizing. So we did the same procedure of standardizing. Usually, you have the standard deviation. You look up the table with the number here, with the z. But we don't have now this number. We have the other way around. We have the probability. So we're going to call the table, and we're going to look up for this figure. It's 0.89, what? 0.8925. So 0.88, 0.89, 0.8925, it's here. Can you see my mouse here? It's 0.8925, which is row 1.2 and a column of 0.4. So what z-score the guy looked at? The guy must have looked to a z-score of 1.24, right? So if I go back, the way the guy calculated this probability is P of z being less than 1.24. This is the way the guy calculated. Now, I know that this z, this little z, came from an operation that I did, right? So this 1.24 is actually the result of this operation of 12 minus 10 over sigma. And now sigma is my only variable, and I can solve for sigma. Okay? So I can solve for sigma. I will do 1.24 sigma is equal to 12 minus 10, which is equal to 2. So sigma is 2 over 1.24. Or 1 over 0.622. Okay? So let's stop here just because this is, it might be cryptic. Because it's the other way around. When you are informed of a normal with the probability and not the z-score, you have to look at the table in reverse. You have to find the figure in the table and then see what z the guy looked at. Okay? So that you can find the standard deviation. Questions about what we did? Good? All right. The last item of our recap, it's item 11. It's the same item as item 9, good approximation. It's the same thing. It's exactly the same thing. It's just now it's with the normal. Okay? So we will let's practice again with an exercise, but it's the same thing. It means that in the continuous, in the continuous world, so in the green world, you have a histogram that looks like a normal. So that smooth curve that fits your graph is a bell-shaped curve. Okay? But the goal is the same. If you want the area of, for example, both of these bins, right? And here is the middle of the bins. In the continuous world, you would have to take the extreme values of the bins, right? So it's the same thing as finding this interval. So let's practice. Consider a discrete random variable x, which can take only even integer values. Okay. It is known to be approximately normal. So again, it's a discrete, but the histogram is approximately, like it takes the shape of a normal with the mean of 50 and standard deviation of 4. If y, now it's another variable. Look, if y, so that was being told about x. X can only take even integers and has a mean of 50, standard deviation of 4. Now another variable, x, is a normal. So it's continuous, right? So is a normal random variable having the same mean and the same standard deviation. It has to have the same mean and standard deviation because it's a good approximation. It fits the curve, the histogram. Find the value of y, and this is capital Y, so that the probability of x is less than 40. So what you want is I want to approximate this in a probability of the continuous world. So let's do that. My discrete variable, here is my discrete variable. It has some histogram. It's a mock histogram that it resembles a normal, right? It resembles a normal. It has a mean of 50, okay? And it goes on only with even values. So it will be like, 52, 54, right? Here you'll have 48, 46, 44, 42, and 40, okay? And 38. So this is the bins, okay, would be like, it's a ghost, and you could go on, right? It's a ghost histogram. I don't have this histogram, okay? But I know the ghost form of the histogram. It's near a normal, okay? It's near a bell curve. All right. So it's asked for us. It said, so this is my x. This is my x. This is discrete, okay? This is discrete. My x can only take these values. It cannot take the middle of the intervals, okay? It cannot. All right. But there is a normal that fits this curve, like that that has the trend of this curve. It embraces the histogram pretty well. Okay? And you want to find the probability of x being less than 40. Okay, so let's zoom up. If you were in the green world, what bins would you be calculating? Would you be calculating the 40 bin? No. No, you wouldn't, because you didn't ask for equal 40. So you will actually start by selecting the curve of the lower bins here, right? Good? All right. So in the end of the day, if you think about your orange world, you're not seeing, like, you want an area. You want an area under the curve that is exactly equal or very close to this green area. Well, where should you start? Where should your variable that can assume the intervals, it can assume values in between 38 and 40, for example. Where should they meet? Where should I start calculating my area under the curve? 39. Okay, so this is an example of another, the jumps are 2. In the other example, the jumps were 5. Now in this example, the jumps are only 2, by 2s. So the middle of the interval is 1. Okay? So in the end of the day, the probability of your x being less than 40 is equal to the probability of your y in the continuous world being less or equal. It doesn't matter, right? You can put less than or equal or just less, because in the continuous world, this doesn't matter. Less than 39. Okay? Now, what would it change if I had asked you this? Equal to 40. Well, so let me, I don't want to. So if the question was this, what would change? Well, you would do the mock histogram, and in green, you would be selecting the 40th bin. So you would want this bin here too, okay? And then your area would come here. So it would be 41. So in this case, the probability would be less than 41. So be careful. It depends, and I'm going to get rid of this, okay? It depends on what you want in the discrete world. What bin do you want to consider in your discrete world? Okay? And you can calculate this if you want. This is now we have the, this is y, sorry, this is y. Y is a normal, right? It would set to be a normal, right? How can I find this probability? Standardize, and then look at the table. Okay? So if I want to find this probability, the probability of y, and again, this is just an if. I'm doing the exercise on top. If you want to find this is a normal with the mean 50 and standard deviation what? Standard deviation 4. I will standardize. So what I'm going to do, I'm going to take from y the mean, divide by standard deviation. From the right-hand side, I'm going to take off the mean, divide by the standard deviation. The left-hand side will become a standard normal, and the left-hand side will be this number here, 29 over 4. It's close to, it's 7 point what? I don't know. 7. My brain is not working anymore. 7, 29. 7.25. So this is P of Z less than 7.25. And then you can go and look up the table. So if you look at the table, it's a huge, well, in this table you won't have it, right? But you have tables that are larger. So it will be almost 1, right? It will be 0.9999999, something like that. Okay? The thing is, these are the steps for good approximation. You can find the interval in the continuous world, and and then you can continue calculating that. If it's a non-standard normal, just standardize and go to the table. Okay? Good? Oh my God, guys, this is not 10, this is 50. Nobody told me anything. I don't know why I put it 10. Why did I do that? Sorry. So yeah, it was too high. The mean is 50. Where is mean 10? I don't know. I just, well, so this is 50. This is 50. This is Z. Then 39 to 50 is 11. 11 by 4 is, I don't know. So 11 by 4 is 2.75. And then you can look up the table. So 2.75. Oh, we have that. Woohoo! 2.7 with what column? This is the column. 2.75. 0.09946. Makes more sense, right? I don't know where I took the 10. Okay, so we're done. Study a lot this week. I'll be here on the test. I don't know the room yet, but I'll be posting it on OWL, so stay tuned. And if you need help next week, just send me an email, or to Audrey as well. Well, Audrey is the RTA. She also will be available. And that's it. I hope that I cannot make you like math just with this course, but I hope that you like it a little bit more than when you came in. And it was a pleasure to teach this course to you. Okay? Thank you so much.